Thank you so much for the warm introduction and to everyone for being here. So this week we are talking about the big, the small, and the complex. And I would say as far as exoplanets go, we're sort of the big across Kavli, but this is sort of the smallest end of the cosmic scale that we get, really, unless you go to the asteroids. And we're certainly also going to be talking about the complex. And so I'll be talking a bit about some of the complexities of these dynamical systems. They are not static, they're constantly changing. There is a lot that is evolving in all of these systems, and we're catching them at various different stages of their lives. So when we're talking about demographics of planetary systems, that's not something that's static. This is something that's continually changing, and that is what shapes my research, is this understanding of how planetary systems are evolving and what is actually causing that evolution. What are the physical laws that are really influencing our planetary systems and shaping what we see today. So if we take this planetary system that's up on the screen and we kind of put it in the middle and then we flip it around, we can learn a lot more about its true properties from its 3D structure. And this is one that is a little bit like the solar system in some ways. So we can see that all of the rings are concentric, they are circular, although we flipped them, and they're coplanar. So you can think of these planets as sort of, if they were on a plate, they would roll around that plate. There are very small tilts between those orbits, but they are pretty close to just all being within this nice 2D plane. If we look at exoplanetary systems, that's not necessarily true. We've seen a lot of planetary systems where we have more complexity, and there are different properties of these systems that can teach us more about how we fit into this broader context. Why is it that our system looks a certain way and we're getting so many others that look a little bit more complex, like what we're seeing here? And one property of this complexity of planetary systems that I've been really intrigued by, and that I'm going to talk about for the first part of this talk, is shown here, where we've now added an extra arrow here, and we've colored the star red and blue. And this is an arrow that is denoting the way that our star is spinning. And in this particular planetary system, in addition to the orbits not lining up with each other, some of them also don't line up with the way that the star is spinning. So our stars have rotation axes. They are going to spin and have a red shifted side and a blue shifted side. And we can study how our planetary systems are oriented relative to their stars as well as relative to each other in order to learn more about what has actually happened in these systems. How have they evolved, and how is that similar or different to our own system? And our own solar system, you may or may not know, is actually also a little bit tilted. So all the orbits, again, are pretty close to coplanar, but they're all tilted by about 6 or 7 degrees. So it's not a very big tilt, but it is significant, and it has been very precisely measured. And if we look at exoplanet systems, though, if we look at hot Jupiters in particular, which are the best characterized exoplanet systems that we have, then we can see that they are far, far from this kind of nice, neat system that we see on top. We have hot Jupiters that do follow that paradigm, but we also have hot Jupiters that are orbiting sideways, that are orbiting backwards relative to the way that their host star spins, which is really strange. We learned that planets form in protoplanetary disks. You usually expect everything to spin together. And so this means that something has happened that has caused these planets to move backwards or to move sideways on these very strange orbits. Amazingly, this is something that we can study. So we've talked a bit about the distribution of planets in terms of their masses, in terms of their radii, and we're getting to a point where we can actually really dynamically characterize these systems and put them into this broader context, not with just the planet properties, but also with their orbital properties and how that shapes the system. So we saw this on Monday in Sarah's talk, this same light curve that is a hot Jupiter. And when we have these planets that are transiting, when they pass in front of their host star, there's a lot more that we can learn. So we can learn about their atmospheres, which we've seen some pretty incredible results related to exoplanet atmospheres already. And in addition, we can also learn about their orbits. So if you take your planetary system and you get a spectrum of your it's mostly your star at this stage is what we're seeing, although we've heard that you see a little bit of planet in there as well. Your star, again, is rotating, and it's got a red shifted side that's moving towards you and a blue shifted side that's moving away from you. And if you have your planet that is transiting, pass in front of a part of this star, then it'll make your spectrum look a little bit redder if it's covering the blue side, or conversely, it'll look a little bit bluer if it's covering the red side. And we can use this slight shift in color that we're seeing from our spectra, to actually learn about the orientations of these systems. So this is something called the Rossiter-McLaughlin Effect. This is a measurement that I've taken across many systems at this point. And this is just showing sort of the types of configurations that you'd expect to see from taking these measurements. So these are radial velocities. You can measure how fast it looks like your star is moving towards or away from you. And as you block out different parts of the star, then you get either a symmetric warp if it's nicely aligned, or you can get these asymmetric signals if your planet is going sideways, if it's going backwards in different directions. So again, we need to have transiting planets to measure this effect, which is why for most of the systems that we see this for, we're talking about hot Jupiters. These are planets very close to their host star. They are very, very hot, and they cover up a pretty good percentage of the host star, at least relative to the Earth-like planets. And there are a couple ways that you can tilt a hot Jupiter system. So if you see one of these, you say, okay, this is very strange. My hot Jupiter is very much not going the same direction as the star. It's not what I expected. You could either say, okay, well, we know that planets form in disks, and if we somehow tilted that disk early on, so maybe there was an interaction with another star or something else that could have actually tilted your entire system relative to your star early on, then you could just form a nice planet within that disk, and you've got a misaligned hot Jupiter, right? So this is one way that you can get this type of configuration. Tilted planets form in tilted disks. And we've seen some evidence that sometimes protoplanetary disks even have different components that are tilted relative to each other. So we know that this at least sometimes is going to happen. We also could tilt them through a different mechanism. So let's say our disk formed, and we had nice planets that just formed. Everything was still continuing to rotate in the same direction. And then from there, your planets can interact with each other. They're often very closely packed at this stage. And you can get something like what we're seeing in this video. So this is the process of planet-planet scattering. Here we have 3 planets in this particular system. It's a nice simulation that just shows over time, as your planets continue to pass each other, to get a little bit too close together, then you can actually toss one of your planets out of the system, which we're going to see in just a moment. And then that tends to leave your inner planet on an eccentric orbit. So it's elongated, it's not on a circular orbit anymore, and that can sometimes be stable and will stay there for a long time, and sometimes it will be a little bit less stable. So if it gets too eccentric, if your planets interact and you launch one of your planets onto this highly, highly eccentric orbit, which, by the way, we've seen. So this is a very famous planet, HD 80606b, that's on an extremely high eccentricity orbit. This is something that happens where you see planets that spend a small amount of time on their orbit getting flash heated by the star. They spend a while away from the star, following Kepler's laws, and it's on this kind of crazy orbit, very, very different, probably, in terms of its climate from what we see on the Earth. And if this happens and your planet is on such an eccentric orbit, it's going to be very unhappy with it, because this is not anywhere close to equilibrium, right? Your planetary system wants to be in equilibrium. So your planet will say, oh no, I don't know what to do. And then it'll remember from Adams and Laughlin 2006 that this is what it's supposed to do in the top right. So this is the circularization timescale for how a planetary orbit is going to evolve, which is dependent on various properties of the orbit as well as the planet and the host star. And it will reach this final semi-major axis, the separation from its star, that's given in the bottom right here. So as your planet is passing its star very, very closely, it's going to dissipate energy, and it will get closer and closer to a circular orbit until it finally circularizes. So this is a process known as high eccentricity migration. This is another way, again, returning to the tilted planets, that you can get a nice tilted planet. And these are 2 processes that are sort of competing. That is a big part of my research recently, is trying to understand which of these is prevalent. Do we get a lot of tilted disks? Do we get a lot of this much more dramatic high eccentricity migration? And remember, in the video, one of the planets was ejected in high eccentricity migration. If you get close enough to form a hot Jupiter, you will probably eject most of the nearby planets. So this could be pretty bad for life. You might get rid of your planets that could have hosted life before they had an opportunity to even get to that point. So it's important to understand what's the distinction between these, as well as what does that mean for all the other planets as well. So if the first of these scenarios was true, then you wouldn't expect, let's return back before we get to the technical slide, we wouldn't expect that there would need to be any relationship between the elongation of your orbits and the tilts. You would form all your planets in tilted systems, whereas on the right, you would actually have a pretty strong relationship where you would need to, at some point, have these very elongated eccentric orbits in order to produce this tilt. So in some work a couple of years ago, I said, okay, let's take all the systems that we have these tilt measurements for, and let's just split them into the ones that are on elongated orbits or that are on perfectly circular orbits, and figure out if we see any clear distinctions between those populations. And what we ended up finding is that hot Jupiters that are on eccentric orbits, no matter what kind of star they're around, are very often spin-orbit misaligned. They're on these tilted orbits very often. Whereas that's only true for hot Jupiters around hot stars if you're on circular orbits. So this is another way that we can look at this. It's, again, sort of a more technical figure. But the main point here is that there's a purple line, and you can see all these lighter colored lines that are associated with uncertainties, that deviates very strongly from all of these other distributions. This is a probability distribution of the spin-orbit misalignment, where 0 is perfectly aligned, and 180 you can think of as a backwards orbit. So we can see that most of these populations, as we're starting to dynamically characterize them, put them into different bins, the ones that are around either hot stars or that are on eccentric orbits, we think of these as dynamically hot systems. There's probably a lot happening in those systems, maybe other planets that could have disrupted them. Those all fall along a distribution where you get a lot more misalignments. That's the green, the red, and the blue here. Whereas the purple line, which is probably the most tidally evolved population, they've reached circular orbits, they have evolved over a long enough period of time that they have also reached tidal realignment, which is when your planet actually forces your star back into alignment with the orbit. In the purple line, that's sort of the only separate population from here. And so really the punchline here is that because we see that a lot of these planets on these elongated eccentric orbits are often spin-orbit misaligned, there's no distinction across stellar type or other confounding factors, it's looking pretty promising that this high eccentricity migration is happening a lot for hot Jupiter systems. And I should mention, you don't need to be too alarmed. Hot Jupiters are only around about 1% of Sun-like stars, so this isn't destroying every planet that we see. But it's important to understand the different ways that your systems can evolve and why it is that we're getting sometimes this kind of configuration instead of the solar system. So far I've talked about hot Jupiters, but if we start looking at other kinds of systems, so it's not just these ones that we can get these tilt measurements for, we can also get them for their neighbors, the warm Jupiters. And there are warm Jupiters that are basically hot Jupiters, but just on slightly wider orbits. So it's exactly what the name sounds like. They're less hot than the hot Jupiters, but not by very much. So a year on a hot Jupiter might be 3 days as an orbit, and on a warm Jupiter it might be 12 days. So they're very similar. The Earth's orbit is 365 days. So these are not so different from each other. It's not the distinction between the Earth and Mercury, for example. And if you look at the warm Jupiters, they seem really weirdly different from the hot Jupiters. They've got lots of friends around them. There are other planets in the systems. And they also are far enough from their star that we don't have to worry about this idea that they might have realigned and the star could have pushed them in different directions, or they could have pushed the star in different directions. We know that if you see a warm Jupiter that is aligned, it probably formed that way. And same with misalignment. It can't really tidally evolve through interactions with its star over short timescales. So during my PhD, I began a survey to just measure a whole bunch of these spin-orbit orientations. These are using primarily 4 to 10 meter telescopes across the US and Chile. And so this is showing the first 10 of these measurements. We now have 19, which was really exciting. And we've just gone out and we said, okay, we want to figure out the demographics of how all these systems are oriented. I'm very proud to have a few of these led by students that I advised. So we have a couple of undergraduates who've actually led papers through this survey, as well as a starting graduate student shown here. So some of the results of this survey that I'm most excited about, maybe the single one that I'm really the most excited about, is that we find that when you look at planets on wider orbits, all of them are actually aligned very nicely with their host star in a way that we don't see for the hot Jupiters. At least if you clean your sample and you say we're going to throw away the binary stars, they can make things a little messier. We're just going to look at single star systems. So we showed a couple of years ago that this is the case for all of our warm Jupiters. That's these little pink-red points that are on the bottom right here. And if you just take random samples from the left, the hot Jupiters, and kind of figure out what's the likelihood that you'd get nothing that was misaligned, we find this is about a 3 to 4 sigma result a couple years ago. Since then, we've been continuing to get more and more of these observations, and the puzzle's been getting even more interesting in that we're seeing even these warm Jupiters on really eccentric orbits. So we're talking E equals 0.4, 0.8, 0.6, 0.8, pretty large eccentricities similar to what we saw for HD 80606. They're still spin orbit aligned, whereas we're not seeing that for the hot Jupiters. So it looks like these are probably somewhat different populations. And most recently, we came out with this paper just a couple of weeks ago. We took another 6 measurements. I'm sort of just flashing by each of these measurements, but each of these is, an entire night of telescope time on the world's biggest telescopes. So we've had a really great time just getting out and getting this data, analyzing it, and figuring out what's going on. We found that even with those, they're also really nicely aligned. So irrespective of your host star type, eccentricity of the planet, any of that, we're still finding that the warm Jupiters are really nice and kind of quiescent. They're all in this nice plane. So what does that mean? Well, if your disks were being tilted, at least the inner disk, so remember I said, you can have inner and outer disks misaligned, but at least the inner disk, if it was commonly tilted, then you'd expect all these populations to be misaligned at the same rate, or it should be maybe a function of stellar type. We're not seeing that. So what that's telling us is that the hot Jupiters are probably forming through this mechanism on the right. And they're forming through a separate mechanism that is misaligning them and causing these high eccentricity orbits. If we look back at multi-planet systems and planets that we expect to have not really undergone any dramatic interactions, the near-resonant systems, then we get a sort of different story, where here we're looking at what's called a Laplace resonance within the moon system of Jupiter. And what we're seeing here is that one of the moons will go around once for every 2 times another moon goes around, and then there's another one that goes around every 4 times that the first one goes around. This is called a mean motion resonance. It's a very stable configuration, and we think many planets probably form in this configuration, and that those resonant chains somehow get disrupted at some point for many systems. So we don't see them across the terrestrial or giant planets of the solar system, although we do have that within the Jupiter system. So exoplanets that show a configuration that is in or near mean motion resonance, we think probably have not been disruptive. They've not undergone planet-planet scattering or anything that would have prevented them from preserving that nice initial configuration. And when we look at those systems, we also see little tilts. So this is reassuring because the solar system is tilted 6 to 7 degrees. And so we are seeing other systems are tilted up to about 20 degrees, and that's pretty typical. You're going to get little disk tilts, but nothing that's dramatically flipping your planets around. As a quick bonus, since I know we'll be hearing about brown dwarfs later from Jackie, I wanted to also mention that we're starting to look at how this extends to other populations. So this isn't just a way that you can understand exoplanets. You can understand binary star systems, you can understand brown dwarfs, and that's what we're starting to probe here. Transiting brown dwarfs are extremely rare. They're very, very difficult to find, but we now know of a couple dozen, and we're starting to be able to actually get these measurements for those brown dwarfs. So a graduate student working with me, Tiago Ferreira dos Santos, recently published the 5th ever measurement of one of these spin orbit alignments for a brown dwarf system. And there are lots more that are scheduled right now, which we're really excited to see, and hopefully this will help us to parse out from a dynamical standpoint, from looking at the orbits of these systems, whether these objects are forming a bit more like planets or a bit more like stars. So far, I've just focused on single systems. So one star, it's got planets around it. But we know that around 50% or more of sun-like stars, at least, we've often got these stellar companions. They're very, very common across the galaxy and the solar neighborhood. And so, okay, if we want to consider these systems as well and not just toss them out of our samples, then we need to also think about how those are organized. And these, again, are very prevalent, and they start to get a little more complicated when you have another star in the mix. So here we're looking at the relative orbits as well as the relative spin orbit orientations of these systems. There are a couple of different angles here, but the first one's the same one we've been looking at, how the orbit is tilted relative to your first star. And we've just got another star, so we're looking at how that orbit of the stellar binary is oriented relative to the orbit of your planet. So needless to say, this starts to get a little bit complex. There are a lot of different configurations that you could see here. But if we take a look at what we have seen, I actually got really interested in this topic because of one system that we took a spin orbit measurement of that had a companion star. And this was a Varm Jupiter. It was normal. It was spin orbit aligned. We were seeing lots of those, but it had a binary companion. And so I went to the ESA Gaia mission database, which does astrometry. This is a mission that just tells us where all the stars are very precisely and where they're going. And so we took a look at the data there, and we ended up finding that the direction that the second star was going relative to the first was perfectly collinear, almost, with a line between the two stars. And what that means is if you take this into an orbital integrator, and try to figure out how the system is configured, it's perfectly edge-on. And remember that we know that all of our transiting exoplanets have to be edge-on, otherwise we wouldn't see a transit. And so this was a transiting planet. It was one that we got a spin orbit measurement for, and we were seeing that both the orbits were perfectly aligned and the spin orbit measurement was perfectly aligned. So if we go back to our picture here, that means that instead of seeing this, we ended up seeing something more like this, where everything was really nicely collinear. So I thought, that's weird. This is the first system that I look at for this orientation, and everything is so perfect. Like, there's no way that this is just a chance, right? So I went in and I said, okay, let's get all of these systems that have spin orbit measurements, figure out how their orbits are oriented relative to each other. And we ended up finding 9 that perfectly lined up out of 40 that we checked. I would say 40 is actually an overestimate because we considered all stellar separations. So some of these binary stars were like 20,000 AU apart, probably just barely bound to each other. And so, but even at hundreds of AU, astronomical units, the distance between the Earth and the Sun, we were seeing that there are a lot of these systems that are really, really nicely collinear. So in addition to seeing this, we also found that they line up nicely in this other direction. And this is really strange because binaries are known for making things messy in planetary systems, right? If you have another star, this is a really nice way to misalign your system. There's one particularly commonly talked about mechanism, the von Zeipel-Ledoff-Kozai mechanism, or the ZLK mechanism, that just warps your orbits over very long periods of time. If you have a companion, then it will allow you to trade eccentricity and inclination back and forth. You're warping your orbits back and forth like what we're seeing here to conserve this Z component of the angular momentum of your system. And so this is something that is commonly known. This is often used as a way to invoke, this is how you misalign a system. But we were seeing so many that were collinear. So I went ahead and I examined this further with a graduate student working at Yale, Konstantin Gerbig. And we said, okay, well, digging into the literature, looking at ideas for how this could have happened, and actually modeling how this could happen at such wide stellar separations, we think what's happening here is that when you have a disk early on in your system, and it's influenced by this gravitational potential from an external point source, it's going to cause your disk to precess. So it's going to precess around the normal to the binary star system, and it's going to dissipate energy because different parts of your disk are being forced in different ways. That some parts of your disk are closer to your external source than others. And so it's going to be trying to warp, but it's going to not want to warp. And so it'll lose energy and get closer and closer to its equilibrium state, this nice alignment. And so you can form nice planets that are aligned with your companion stars through that. Konstantin did a great job of modeling where we expect this to actually work with physical disk parameters. So we went ahead and we said, okay, well, this can't work at infinitely distant stellar separations, right? Your star is so far away that it feels, the first star feels almost nothing if it's 10,000 AU apart. So in what cases should this work? And we found that it works out pretty nicely out to about 800 AU, where we see this trend falling off, and where a couple of other papers have also seen this trend falling off, if you assume pretty big and or pretty viscous disks. So this is kind of in line with this idea that maybe the disks are a little bit bigger, a little bit more massive than had been initially thought from these observations that we see directly the gas and the dust of those disks. If this really does work well, then you would expect it to be more important for some systems. So if your second star is really massive, it's going to have a very important gravitational influence on your first star, whereas it'll matter less if it's a low mass companion. And so you can sort of see that here, where you push everything to the left, you push it all to alignment if you have a really massive companion star, and it becomes less and less important at wide separations as you go to the left. So we dug into the data, looking at data from the Transiting Exoplanet Survey satellite mission, also using a control sample to make sure that we believed our results and this wasn't something related to our processing of the data. And we ended up finding that, indeed, we were seeing that the planets that had higher mass secondary stars were actually doing a much better job at aligning than the ones that didn't. And so this is something that is really exciting and interesting. These binary companions can actually, in addition to scrambling up our systems and making them much less pleasant places to be, they might actually, in some cases, help to create a more orderly system that is more quiescent. I wanted to mention that we're not seeing this everywhere. So we know there's a reason that the ZLK mechanism is very famous. We are certainly seeing it in at least some systems. And in our sample, at least, with primarily hot Jupiter hosts, we're seeing that this is pretty prevalent around cool stars, but the hotter stars show no clear trend. So there's probably some relationship here that's maybe not so well probed by our small sample, where we're seeing that some of these systems are undergoing these Kozai lead-off, von Zeipel lead-off Kozai oscillations, and some of them aren't, and some of them are dissipating that energy and getting closer to this plane. So this is kind of the two paradigms that I've put forward, and we think that probably both of them are happening, and there's going to be not necessarily an even distribution between these two. I think there's a lot more to do that would be really interesting to understand in what systems are you getting this alignment versus this misalignment, but we're certainly seeing signatures of both of those. So the last thing that I wanted to mention for just looking at 3D geometries of planetary systems is that in addition to looking at these orbital geometries, if you look at the planets themselves, they're also not actually perfectly round. So you can see I made the red one here just slightly oblate. So we know that in our solar system, Saturn is actually not perfectly round. Saturn is spinning fast enough that it's a little bit fatter at the sides, and it's kind of shorter in vertical direction. And this is about a 10% deformation because of Saturn spinning quickly. This is something that we expect to see for exoplanets. Nobody has actually had a very, very strong detection of this yet, but this is something we expect with current era instruments, with JWST, to be possible. So I couldn't help but put this in because this paper it was just published about a day ago by my graduate student, Ben Casses, who's developed a new Python package to actually go ahead and do this modeling and actually show that we can distinguish the signatures of these oblate planets from those of planets that are just perfectly spherical. So it's a really beautiful package. If you do exoplanets, I certainly encourage you to check it out. It's got some beautiful visualizations. So here we're showing just an example of what a transit would look like for a perfect sphere versus a triaxial ellipsoid if it's just a little bit oblate. And you can see that the transits on top look almost exactly the same by eye, but if you subtract one from another, then there are distinctions that you can see that will depend on the orientation of the system, if it has an obliquity that's non-zero, as well as how oblate it is. And here we're just saying an example of a visualization for a tidally locked planet, that the same side of the planet's always facing the star. All right, so I wanted to end with just a little bit of a word about the Habitable Worlds Observatory. So HWO is a mission that has been kind of alluded to a couple of times here and there. This is NASA's next flagship mission that has been selected as something that will hopefully launch in the 2040s. There's a lot of effort that's going into development for HWO. And I personally am working on the demographics and architecture science cases for HWO. So I'm really interested in understanding the diversity of exoplanetary systems and how we're going to be able to probe that from a space-based direct imaging mission. So this will be 6 to 8 meters in size, covering a pretty broad wavelength range that is still being determined. And many of the people that I work with on HWO actually came directly out of Dave and Sarah's group. So in yellow are some of the folks who have worked directly with Dave, and in pink are some who have worked directly with Sarah, who are on the leadership positions that are the people that I interface with directly to make this mission happen. So we're really standing on the shoulders of giants. This is the next generation of, this is launching in quite a while. We're just starting to formulate it. But we're really empowered to dream tremendous dreams because of those who not only set a foundation, but who also continue to push ahead at these frontiers every day. So with that, I will conclude. Planets, we think, generally are probably forming in these nice aligned configurations, but that's not always the case. And so it's useful to figure out when that does happen, when you're getting a hot Jupiter, something very unlike the solar system, versus something that is more like it. Stellar companions, maybe contrary to popular thought, actually can help to push systems towards alignment rather than just disrupting them. And by putting together this picture with various planetary systems at different ages, different configurations, there's a lot that we can learn about our own solar system in a broader context, as well as just for the sake of fundamental science, understanding this incredible universe that we live in. So, thank you.
Yeah, it's really great that we have bright young scientists who can, in the future, with the Habitable World Observatory in 20 years from now, really be leading this. Some questions? Sarah?
I have a two-part question.
Yes.
Part question. So these hot Jupiters in your models, they clean everything out, is that right? Like as they move in by whatever mechanism, they get rid of everything.
They clean out the inner system. So there can be outer planets beyond where the hot Jupiter started.
And when they're cleaning it out, what's happening? Are you getting like an asteroid belt or an Oort cloud? But I've got a two-part question, so that's the first one.
That's a good question. So I don't directly model this, but the inner planets are either thrown into the star or out of the system most of the time. It's possible you might end up with a belt sometimes, but my understanding is they mostly end up getting ejected out of the system, so you wouldn't have that material left.
I see. So this other question may be a bit outside the realm of this, but in terms of Habitable Worlds Observatory, when we're thinking about searching for a planet, one of our biggest problems is the zodi, because as the planets are forming and moving around, so I'm not sure if you can answer this question, but I was specifically wondering if you don't have a Jupiter, what happens? Because supposedly our Jupiter was responsible for our asteroid belt, for making it, and then for disturbing it, which gave us volatiles. So I'm wondering what on the team has discussed this, whether it's going to help us navigate or predict how much zodi we're expecting, and if there's no zodi, because there's no giant planet, how do we get volatiles?
Right. I would say this is a pretty open question, and I'm hoping that actually facilities like the ELT might help to actually put better constraints on what degree we should expect these zodi to be contaminating the observations that we're getting. This is something that is not so well constrained observationally at this stage. It may be that if you can determine whether there are Jupiters in those systems beforehand, you might be able to at least make some prediction for the level of zodi that you expect. You can also look at infrared excesses and try to see if there's some small signal. But it's something that a lot of people are concerned about for HWO, is the level of contamination that you get from the Zodi. And we're hoping that there will be a lot of constraints that will lead up to it so that we know what to expect. But it's something that there are certainly others who are on other parts of the team that are working very intensively on that particular aspect of the systems.
So did I remember right that it's the hot stars that are not aligning their systems and the cool stars are?
Yes.
Do you also see a difference in the typical planet architecture between the two types of stars? Like, do they form more or less giant planets?
So there's certainly a metallicity correlation, which I believe it's been shown that it's stronger with metallicity than with stellar host type. So there is some correlation that's seen there. Yeah, so you're going to see probably some more hot Jupiters around at least the more metal-rich stars, which are often also more massive.
And were you able, for the ones in your sample, did you have a system? Do you know what the planets are doing in those systems?
Do we know what the other planets are within the systems?
Or do you just know the hot Jupiters?
For some of them, there are companions within the systems, particularly the Varm Jupiters. So some of them fall in the Varm Jupiter range, and they commonly have companions up to, I think there's actually a lower limit of about 70% of them have companions. So some of them do have companions, and there aren't enough systems in the sample that I'm currently looking at to really parse whether there is a stronger trend in alignment versus misalignment with the companions as well. But I think that's a really interesting direction that, especially if you're stacking a lot of systems, doing it at a statistical level with these transiting surveys, maybe Roman will be able to help. This survey that we were looking at was mostly looking at TESS. Then you might be able to actually parse that as well.
Great talk. So you mentioned that for binary system, stellar system, in some instances you have multiple system planet that remains quiet, right, because of the alignment. So I wanted to better understand what are the conditions so that the systems remain quiet. And I wanted to know whether this is rare or this is common.
Yeah, so if you're pushing your systems towards alignment, then it helps to have very big disks, or disks that are very efficient at dissipating energy, which means high viscosity disks. So those are the main parameters that are going to matter a lot in that model, and they, again, aren't so well observationally constrained, kind of order of magnitude at this stage, but you might be able to then infer from what kinds of systems you actually see this alignment in, what those properties are from the disks. So it's kind of a back and forth conversation with the disk observation community as well to figure out to what extent are we constraining those systems. And something else that may be playing a role is you could leave a lot of these systems behind that didn't undergo Kozai-Lidov oscillations, and they end up looking relatively flat. So then there's the question of, do the systems look even flatter than you would expect, or is it just that all the other systems are undergoing von Zeipel-Lidov Kozai oscillations that destroy all of the coplanarity that we're seeing? So I think there are a lot of open questions, and it's something that there are a couple of teams that I've been working with the team at MIT, so Andrew Vanderberg and his team, but there's also a team at UT Austin that's exploring this, and I think there's a lot to be done to understand the exoplanets and the binary system specifically.
I was wondering, in this two-body interaction that leaves one giant planet behind and the other one is ejected, are there some specific mass ratio between the two for this to work, or does it work with pretty much any types of planets?
So you tend to eject the lower mass object. So you would generally need to have multiple giant planets.
In order to put the giant planet, the remaining one, on an eccentric orbit and then do this thing to migrate inwards, you also need to have a relatively massive other object, because little tiny things don't eject big Jupiters, right?
Yes, that's right. So we're looking at, it is only about 1% of systems that actually create these hot Jupiters, but we're looking at potentially the highest mass systems that are creating multiple Jupiter-sized planets.
Thank you.
Thank you.